Okay, let's see, is this going again? Okay, so let's get started for the final lecture of the semester. Okay, everybody's happy. What else do we have to do in here? We have you have your homework 5 is due today. If you haven't used your extension, you can turn it in at the final. Okay, so that's what I want to, yes?
Two questions about that. It doesn't affect me, but what if one of the teammates had used it?
If there's one did, one didn't, figure out something that's fair, write a note on it, and we will decide if it's fair or not, and then deal out appropriate punishment if it's not fair. Yes?
Do we know the location of the final?
Okay, so where is the final? What is the story of the final? The final exam is going to be, and correct me if I'm wrong, on Monday. Okay, May, I believe that is 20th. Is this consistent? It is going to be at 5:30 p.m. and the room is going to be Benedict, is what they have told me. Now, Benedict, as I understand, somewhere on campus there is a place called Benedict Hall. Is that right?
Yes.
Okay, how many people are aware of this place? This is an uncharted part of campus for me. But I gather it's like a dorm, right? Is that right?
Yeah.
Okay, so I am told that that they are converting some area in Benedict to a place to give an exam. Okay, so yes.
It would be where Benedict Dining used to be.
Where Benedict Dining used to be. Okay, so is that big? Had anyone ever had a final there before? Yes, and was that a big area?
Yeah.
Okay, it's an okay place to take a final, right? Okay, so we will be at Benedict. The place to be is Benedict. Benedict. I think there was a recent pope named that. Benedict. And it is going to be in the H quad. That's what I am told. So, you will show up there. It will be like the midterms. You will have 2.5 hours. It will be something like on the order of 9-ish problems. Okay? So, a little bit less in principle than 2 midterms. It will be the equivalent of about 1 problem per subject we have covered. Okay? So it is comprehensive. Okay? A bad thing to do would be to spend all your time studying about NP-Completeness unless you understood everything else before that. Okay? It's good to review these things, think about it. Hopefully we can get it clear the second time. That sometimes happens. Okay? Yes? Is there going to be an answer key released for the last homework? The answer is, I certainly hope so. Okay, so I intend to. Okay, and when that's released, it'll be released. It'll be on the webpage. Yes?
So we're not going to separate rooms?
You are right now going to go to Benedict, and if I need to put you in separate rooms, you'll be in Benedict. Okay, I believe there is enough space. If the class wants me to punish the people who did not go to a separate room yet, we'll find the worst part of Benedict and put you people there. Okay? But that's what I am told we're going to do. Any questions about that? Okay. Any questions about the exam arrangements? Where are we going to go for the exam? Benedict. I didn't hear that. Where are we going? Benedict. Okay? And I'll send out an announcement to this. I hope to remind people. It'll be on my webpage. Be sure you're there. And tell your friends. Any questions? Okay, any other questions about the final exam? What's going to be on it? What is it going to be like? How do you study? Okay, question. Yeah, question. No. Again, it's like the midterms. I recommend studying homework problems that we've done before is a good starting point. Make sure you understand them. Other problems in the book. The majority of the problems in here, I will promise, will come from the book. Okay, in some flavor or not, but if I won't guarantee that all of them will. Okay, that's my intention, like the other midterms. Yes. It will be about 9 questions, so you have more time than a midterm. It is going to be the equivalent of a little less than 2 midterms, is my vision. Okay. Any questions? Okay. Figure 1 problem per thing we have done. Okay. Any questions? Any other questions about the final or logistics or anything like that? Okay, again, the grades have now been posted for all the assignments and daily problems that we have to date. I want people to go and check what you should check to see what we have them properly recorded. If you find we do not have them properly recorded, okay, what I recommend that you do is you can send me a message if you want. But more helpful is if you have a paper, for example, you got back with a different grade than what we recorded you for, bring it to the final and show it to me, and we will double check that. Okay? If you have some other issues, we will either resolve it at the final, or you can mail me in the TAs. But I think we are basically honing in on getting things right at this point. Any questions? Okay, and again, everything will be curved at the end, so don't panic, just do the best that you can. Any other questions logistically? Yes? How is the grade distributed? Okay, so I mean, again, I am going to curve, and I will distribute it on a curve. I recognize people like to graduate, and I recognize this is a requirement that people get a certain grade above something in order to graduate, and I don't like to stand in the way of that. Okay, so that in that sense, that's what I'll say when I curve. Usually, I would say I put the median at about B minus. Okay, that's I guess the basic story. Okay, any questions here? Okay, again, if you've been doing badly, it would be nice to do better on the final. Any questions? Okay, good. Okay, so let's go on. We're talking about NP-Completeness in here. We've been bandersnatching and mobility, okay, for a long time. Let's see how we start to prove things NP-complete, okay? And the daily problems are good examples of something that's not so hard that you might not be able to see this reduction, but maybe it's not obvious at the beginning, okay? So what is the hitting set problem? The input is a collection of subsets of a set S, okay? It's a set of elements. Let's say you might as well consider integers, okay? And we have a positive set integer k. We want to know, are there k elements we can pick such that each subset contains at least one element from our chosen set? So what does that mean? Let's say that there are n students in the class. We'll number them 1 through n. They're all distinct students. And let's say that you have different groups of people. Okay, maybe there's a group of people who live in H quad. Okay, person 1, 4, 17, 23. Maybe some of you are members of the Crips. Okay, those people, 1, 17, 26. The Bloods. Okay. Okay, people who are AMS majors, hopefully not too many of them. CS majors, probably a lot of them. Okay? My goal here is I want to be able to pick a small number of elements, representatives. Let's think of them as representatives. I'd like to pick a group of people such that every organization has at least one person from that organization included. Does everybody see what the problem is? I want to assemble a student senate here where every subset of students has at least one representative in the Senate. And yet I want my Senate to not be too overwhelming. I could put all the students in the Senate, but that doesn't do me any good, right? I want a small subset, a subset of less than k people, such that every one of my groups has at least one representative in it who is in my Senate. Okay? That's what it means to be a hitting set. How many people understand the problem? Any questions about that? Okay? So, question?
Can a student represent multiple groups at once?
Yes, a student can represent one. So if you have one person who happens to be a Crip and a Blood and a CS major and an AMS major, that one person can be a universal Senate. Okay, that's the exact point. Okay, if they had to be distinct, one person, we want this one person to cover as many groups as possible, right? Any questions here? Okay, so what is the goal? How do we do this problem? Any questions about what the problem is? Okay, so if we want to prove this problem is hard, that's what it seems to want us to do, to prove it is NP-complete. What problem do we know about that is a good starting point? Okay? Is it SAT? Doesn't smell like SAT. Is it vertex cover? See, a lot of people nodding. Why does vertex cover smell like this problem? Somebody who had their hand up. Why does it smell like that? Yes?
Because we want a subset and because of the K variable.
Because, again, we want a subset of size of K. That's sort of what the vertex cover said. But that's not enough of a similarity for me to really see a similarity, yeah? Because we want to cover, in some sense, all the different groups. Okay? In vertex cover, we want to pick vertices that cover all the edges. And here it seems we want to pick elements that cover all the subsets. Does everybody see that? Now I see an analogy forming. In fact, if I believe that, what is my analogy? Let's start to write down my analogy a little bit. For vertex cover, I want to pick vertices to cover edges. What about hitting set? What is that going to be? I want to pick elements, okay, to cover what? Subsets. Okay? That might now give me an idea of what I want to do. Okay? I've got to now I've got a sort of a little bit of an analogy here. Okay? And that I probably want my elements to correspond to vertices somehow. Okay? And my edges to somehow correspond to sets. Okay? Does that make sense? Subsets. That might be what I want to do here. Maybe, maybe not. Okay? Any questions? So how would I proceed? I'm going to proceed by, you have told me that you want to solve vertex cover. Vertex cover takes as input a graph and a G. Okay? You want to solve it by your mobility is going to be hitting set. And we're going to be including, there's a universal set, there are subsets, okay, and there is a bound, let's just call it K prime. Okay? What should these things be? Okay? Any ideas of how we can make this reduction? Okay? Yes? So you want to say the universal set is going to be V1 ... Vn. That's what you're telling me. Let's think about that. What else is there? So you want to say that every subset are going to be, each subset is going to be an edge x, y, right? Each edge, you're going to tell me, has only two, it represents a two-vertex subset. Does everybody see it? Vi, Vj. And you want to tell me that K prime, the number of things you want to pick is what? K. Let's think if this reduction makes sense. Okay? She is saying, I want to find a hitting set for this particular element. In order for me to cover this set, this particular two-element subset, it's a very small subset. Maybe that'll be the crypts. I don't think we have too many of them here in the class. Okay? So, two of them, okay, if you have to get one representative, it had better be this one or that one. Does everybody see that's what it means? In our hitting set, to cover this edge, this two-element subset, we need to pick a vertex, one of these two vertices. So what hitting set is saying, find me the smallest number of vertices such that every edge has at least one representative. Right? That's exactly what this transformation is saying. And that is exactly what vertex cover seeks to have done. Does everybody see it? Vertex cover says, do there exist K vertices such that all edges are covered? With this particular hitting set instance, anytime you find K prime, meaning K, vertices, universal set elements corresponding to vertices, that covers all the edges, that's a hitting set, and that is also corresponding to a vertex cover. Do people see that this is the transformation? How many people see it? How many people don't see it? How many people don't see it who want to see it? Okay, any questions about that? A question like I didn't get it is a good one. Okay, we're making an analogy. The important thing here is we're translating the problem so it says the exact same thing. That's exactly what we are doing. Vertex cover problem says, do there exist k vertices such that every edge is covered? Hit says, are there k things from this set of vertices such that every one of our edge sets has one vertex taking care of it? Okay? That is saying the same thing two ways. Therefore, the hitting set on this is going to be true. There is a hitting set of this size if and only if there is a vertex cover of that size. That is the reasoning we have to see here. Any questions about it? Okay? This NP-Completeness thing is about making analogies. Okay? We are translating the hard problem into a specific instance of the problem we are interested in, our mobility, such that the answer to that particular mobility instance solves that particular vertex cover instance. Any questions about that? This is the kind of thing I'd like you guys to be able to do on an exam. Okay, one of this kind of stature. Okay, yes?
The vertex cover, each set of collection C would represent what vertex cover? Each edge?
Okay, so in this particular case, what are we saying? Each subset is an edge. So in this particular case, let's rewrite this hitting set thing. Does S contain a subset S prime? Okay, this means, S is the collection of vertices in our reduction. And the collection of subsets, C, these represent the edges. Okay? Does there exist, a subset of the vertices that is at most size K, such that every edge contains at least one element from these vertices? Once you have translated it, that's exactly what vertex cover is saying, right? Once you have made the analogy between S as a collection of edges and U as the set of possible vertices, you can pretty much read off that question as exactly being vertex cover. Okay? Hitting set can be used to solve vertex cover. If we had a fast algorithm for solving hitting set, boy, we got a fast algorithm for solving vertex cover. But there is no fast algorithm for solving vertex cover. So therefore, this means there can't be, there can't be a fast algorithm for solving hitting set. That is the reasoning that we're doing here. Any questions about that? Any questions about this one at all? Okay. Any questions? Going once? Twice? These are the kind of reductions I'd like you guys to be able to try to figure out. Okay? Any questions? Yes? Okay, so on the exam, it is perfectly fair for you to say, Skeena showed vertex cover was hard. Therefore, it's my Bandersnatch. I do not expect you or want you to try to reprove that vertex cover is hard using this ghastly construction with the triangles and that kind of thing. Okay? Once you can start from any, either if I say you can start from any hard problem, you start from any hard problem. If I say start from this one, it will be because I think there is a nice, easy way to see the analogy there. Okay? Does that answer your question? Okay, good. Any questions? So this is the answer. You write this down, you get credit. Okay? Ideally with an explanation of why this is the analogy. Okay, so in case we can't read it, you should know what your ideas are. Any questions? Okay, let's go on a little bit. Okay? So let me, again, this notion of how do you see these analogies may sound very, very hard. It's one of these things that, again, when you first see it, and it takes a time to get used to this idea, to see it, to see enough examples. Okay? But once you know what you're doing, these are, there's relatively routine ideas that go into making these kind of analogies. Often, okay, one of the easiest ways to do is to show that your if you want to prove a problem is hard, okay, one of the easiest way to do it is you want to take your problem and show that even if you take a very special case of it, it is a hard problem. So let's consider the problem of, does a graph have a path of length k in it, where you visit k distinct vertices without repetition? Is that problem hard? Well, the Hamiltonian path problem of given a graph, visiting all the vertices once without repetition, that's a hard problem. If it is hard to find whether the graph has a Hamiltonian path, okay, meaning visiting all the vertices, then you ask me, is it hard to find for a given k? If I set k to be all the vertices, then that's Hamiltonian path. Okay? So that is, maybe the easiest and most common way to kind of reason about it. That your problem is, a special case of it is one of our famous hard problems. Okay? Sometimes you can get away taking the structure and making a few local little changes, and then it suddenly becomes obvious it's a different problem. I don't think I want to tell you about this particular construction, but maybe that's what you kind of need to do. Sometimes you get into these ghastly, horrible constructions that we talked that I've shown you, like for vertex cover from SAT, or integer partition from vertex cover. But even as I'm going to try to show you today, these ugly, elaborate constructions usually have some logic to them, and that you can kind of maybe go through them. If you've seen enough of these things, it's not a miracle to prove something's hard. Any questions? Okay. So in fact, what I'd like to do now is just give you my advice as a prover of NP-Completeness, of showing problems hard. What how I go about doing it. Because, again, it's not as tricky as it looks. I don't expect you to master it and be whizzes at this by, after just a couple of weeks of practice here. But learning to be able to see when you're given an algorithm problem, gee, this thing is probably hard, and it smells a lot like some of those other hard problems we've talked about, is a very useful skill to have. Okay, and that's what I'm trying to develop here by giving you this session on NP-Completeness. So how do you prove things hard? Now, the one reason why I think it's easy and you think it's hard, okay, difficult to do NP-Completeness proofs, is because if you think about what an NP-Completeness proof is, it's an algorithm, a code for translating the input from one thing to another thing. And when I do an NP-Completeness proof and I show you my reduction, you are in some sense trying to understand my code for doing the translation. If you are given a piece of program that somebody else wrote for solving a problem, what do? Do you try to read and try to understand it? Or do you give up and throw it out and rewrite it? Okay? Most of you, I imagine, are good enough software engineers. You give up with what the other guy, crummy code the other guy wrote, and you rewrite it, because it's easier sometimes to write your own thing than it is to understand the details of something somebody else has done. This isn't making sense to anybody. Okay, I think a lot of, and there's a similar notion here. I find that it's usually easier when I read a printed NP-Completeness proof. My God, there's all those variables, and there's, what are they doing? Okay? But there is a logic to what they're doing, and it's usually easier to try to find it than to figure it out rather than try to understand exactly what they were doing. Okay, here is my advice. If you want to prove some problem hard, you have to start from a problem. You're going to be doing what? You're doing a Bandersnatch-Bobilli thing. Bandersnatch, calling Bobilli, right? If we want to translate all instances of Bandersnatch, the simpler Bandersnatch is, the easier it is to transform that into another problem. This is logic. I want people to understand the strategy here. If I have a choice of transforming sat to something, or 3-sat to something, 3-sat is better. Why? Because any sat instance includes 3-sat instances, but it includes other things. If I'm going to write a program to translate that into something else, it's going to inherently be more complicated than if I was just translating the 3-element clauses, right? Does everybody see that? The simpler, more specific problem you use as your Bandersnatch, the better off you are, okay? Any questions? So some people in here sometimes said, well, how would I prove something is hard? Well, traveling salesman is a hard problem, right? Why don't I use traveling salesman as a Bandersnatch? I have never in my life used traveling salesman as a Bandersnatch. Why is that? Traveling salesman asks what? Given a weighted graph, find the tour of a given weight. Well, that's fine. But there's a simpler problem that smells like that. Hamiltonian cycle. Given an unweighted graph, find a tour that visits all the vertices exactly once. This problem is also NP-complete. Okay? And it's simpler than traveling salesman. It doesn't have weights on it, right? So it's easier to translate it. And as I keep studying this, I know that there are simpler things than Hamiltonian cycle. Hamiltonian path means it doesn't have to close back into a loop. That's also NP-complete. Even Hamiltonian path on a directed planar graph where each vertex has total degree 3 is NP-complete. So what do? I start from the simplest version of a problem I know about and then do the transformation from that. Okay? Everything's equally hard, and the simpler the problem you start from, the more likely you will achieve success. Any questions about that? That should be clear in logic. Any questions? Okay. What about how do we prove? We want to prove Bobilli is hard. Okay, right? How do we make prove that Bobilli is hard? Bobilli, we have to take every version of our Bandersnatch and translate it into a Bobilli, right? If we can't find the transformation, the more powerful we can make our Bobilli problem, the easier it is potentially to do the transformation. Let's say you're trying to transform Bandersnatch to Bobilli and you can't figure it out. Maybe you can translate Bandersnatch to weighted Bobilli. What is a weighted Bobilli instance? Well, whatever the things that Bobilli is made of, add weights to it. Okay? This is a more general problem. Okay? It is probably easier to translate to a more general problem. So if you're trying to prove your problem is hard, don't be afraid to make it harder. Okay? Add extra constraints, extra freedom, add weights, things like that. And maybe that will be easier to convert all your things to. Okay? And then once you've done that, maybe you can figure out how to get away from that. Do people understand the philosophy here? Okay? Okay, you're trying to use Bobilli as this big black box to solve your problem. The more powerful the black box is, the more easier it is for you to figure out how to use it. Okay, any questions? The other thing that's very important is you have to select the right source problem for the right reason. Select the right Bandersnatch. Okay? And there are a couple of schools of thought of how you would select your Bandersnatch. One is you go to a book like this that listed at one point all the known NP-complete problems in the universe. And you look through hundreds of pages and saying which one is closest to it. Okay, that's how an amateur would do it. Okay? I will tell you that I personally use only 4 hard problems, pretty much all of which you know about, in doing all of my NP-completeness reductions. Okay? Because there are only basically four kinds of Bandersnatch that I will use. I can know a lot about them. I'm familiar with them. And it makes it easier to know what special versions are available. I will use 3-set when nothing else applies. Okay? That's my general thing. That's the old reliable. If I have a number problem, okay, I will use the integer partition problem we talked about. Is there a subset of numbers that adds up to something? That we talked about last time. If I have a graph problem where I am looking to, the hardness seems to depend upon selecting something. This is what I mean by subsets. Vertex cover, stuff like that. If I have a problem where there is something where I am picking subsets of things, that is probably what vertex cover was meant for. Or it's closely related problems like independent set and clique. Okay? Any questions? And the final class of hard problems that I deal with are where there are graph problems where the hardness depends upon ordering things. That is usually a Hamiltonian path, Hamiltonian cycle-like problem. And these are the only 4 basic Bandersnatches that I will consider using. Okay? Any questions about that? Okay? Because I know these problems, I'm familiar with them, and and it becomes, with more and more practice, you get better and better at it. Any questions? Okay, good. What else do I do? How do I think about trying to do these transformations? I am looking for analogies between problems. I am trying to make this look the same as that. Okay? And, I am trying to translate them while making them stay the same as possible. Okay? And the way I think about this, and maybe, you have to think about what kind of structures can you build into the translation that makes sure that the optimal solution wants to do what I want it to do. Okay? So I like to think about, my kind of reasoning when I'm thinking about these things. I'm trying to do things like this. I'm saying, well, after I translate it, if you pick this for your Bandersnatch solution, then you're also going to have to pick all of these things. And that's going to be undesirable, and that's going to force you to do what I want you to do. Okay? So maybe this is still a little too abstract. Okay? But I'm trying to think at a logical level. Okay? What I can do to force the optimal solution to the translated problem be the same as the optimal translation solution of the original problem. Any questions about that? Okay? Good. And again, what do? I am thinking strategically at a high level. What do I want my translation to do? And then I'm building little features and gadgets and things, little structures of translation to do what the big pictures I want it to do. Okay, again, this may still seem a little airy, but this is the way that I'm doing my thinking about things. Any questions? And my final advice is that if you are given a problem, you're trying to prove it is hard, and you can't prove it hard, there is often 2 reasons. One is you haven't figured it out yet, but the other is maybe there is in fact an efficient algorithm for it. And so what happens to me as an algorithm designer, what do? When confronted with a new problem, I start trying to design an algorithm. Oh, is it shortest path? Is it dynamic programming? Is it sorting? And if I can't figure it out, I say, well, it must be hard. So I start trying to prove it's hard. And I say, okay, well, I try to think, why is this like a SAT problem? It's sort of like that, except, it's not like that. Why is it like a vertex cover problem? Well, it's not like that. Oh, the reason is because it's in fact a minimum spanning tree problem. And in fact, sometimes when you alternate between trying to prove it hard and trying to come up with an algorithm, you can often get better insight into either why the algorithms don't work or the problems are hard. Any questions here? Okay. Fair enough. Kabunk. Now what I'd like to do, that's all my philosophy. Let's stop talking philosophy. What we're now going to do is my NP-Completeness challenge. I have a copy, he's even got a copy, of this book called Computers and Interactability, which was a list of all the NP-Completeness problems in the universe known to a certain point. After a while, people kept proving more and more, and these guys got tired of writing a book, and so... But there's a lot of the most important NP-complete problems are in there. Somebody who's got a computer, okay, and on the web, can you go to the course web page? Okay, let's just try to do it. It's probably easier for you to do. Go to the course web page, and on there is a link there that says a list of hard problems. Okay? You pick another student in the class. You pick a different student in the class. Okay, who's been picked? Somebody's been picked. Okay, good. What groups of problems are there? Now what groups of problems are there on that list?
Graph theory, network design, set partitions, storage and retrieval, and mathematical programming.
Okay, which of those types of problems do you want to look for? Let's take a class. Who wants to look at a graph theory problem? Raise your hand. A couple people. Who wants to look at a network design problem? Raise your hand. Who wants to look at what was the next one? Sets and partitions problem. Raise your hand. Sets and partitions seem to have a big crowd today. What's the next crowd? Storage and retrieval. Who wants that one? A few. Is that it? Mathematical programming. Okay, what is the crowd? What do people think was the majority? Mathematical programming. How many mathematical programming problems are there? 3. Pick a number from 1 to 3. 2. What number problem is it? MP9. MP9. What is MP9? You have the book. Can you tell me what problem MP9 is? I also have the book, but let's see what MP9 is. Okay, let's see if we can understand this one. Again, I haven't looked at these for a long time, but I tried to list a bunch of problems I thought, what? Knapsack. Let's think what this problem means. What does knapsack mean? Okay, let me just look this up so I can read it, just to make sure. What page is it? 247. Okay, 247. This one, I think, if it's knapsack, it's probably going to be a pretty easy one. Okay? So what is this problem asking? Let's go back to this one. This is called the knapsack problem. It says that we are given as input, okay, what does it say here? We are given a set of elements where each element in this set has, it looks like, a size and a value. Is this right? Let's look at this thing. So he's saying that we've got a collection of objects here, n objects, okay, such that each object has a size and a value. And we are given a constraint on the size of our knapsack, okay? We have K, which is the size of the knapsack, and we've got a, a B, which is the desired value. What? Okay, B is the bound of the knapsack, and K is the amount of value we want to try to get. Okay? So what is the problem here? Let's make an exact instance here. Let's say that we are given, okay, a knapsack with a capacity of 10. And let's say we've got objects. Each object has a size and a value. Let's say we've got a $2 pound element with a value of $8. Okay, a 6-pound element with a value of $15. A 5-pound item with a value of $12. Okay, what other ones let's come up with some other things. Let's say a 4-pound object of, let's say, $3. And let's make the bound 8, just to make it more interesting. Okay? What is the most valuable thing I can steal for a total of, at most, 8 pounds worth of stuff? Okay, do you see what the problem is? I'm given objects, how heavy they are, and how valuable they are. And my goal is, can I steal greater than K dollars worth of items where I only take 8 pounds worth of items? Right? Does everybody see what the problem is? In this particular case, if I'm walking out with 8 pounds of items at most, how much stuff can I steal? Okay, what is the most value I can get from it? Okay.
What's the second number? Dollars?
This is $8, $15, $12, $3. This is pounds, 2 pounds, 8 pounds, 5 pounds, 4 pounds. Okay, what's the maximum amount I can steal? Yeah? You're saying get $23. Well, how do I get $23? First and second one, that will be 8 pounds, and I get $23 worth of stuff. Does everybody see that? Okay, and I filled my knapsack, and I will have come out with $23. So the answer here is K greater than or equal to. If K was, so long as K is less than or equal to 23, the answer is yes, I can steal more than that much money. If I say, can I steal $24 worth for 8 pounds of knapsacks, the answer is no. Okay? How many people understand the problem? Okay? How many people don't and want an explanation again? Okay? So let's look at this one. This one I think is going to be very easy, actually. Which one of our chosen problems is it that smells most like knapsack? Is it satisfiability? Is it vertex cover and its cronies, integer, independent set and clique? Is it Hamiltonian cycle? Or is it integer partition? Okay, yes, we talked about that one. That was the one with the funny incidence matrix that got everybody scared last time. What was that problem? That problem, if I remember correct, let's now go and... does everybody remember what this problem is? I'm going to go to clear it now. Any questions? Clear. Bunk. So what was integer partition, if we remember correct? Integer partition, if I remember correct, gave me a set of integers, S1 through Sn. And I was given a target. And the question is, does there exist, a subset of these things that adds up to be exactly equal to the target? Right? That's what subset sum was. Right? How many people understand what subset sum is? How many people understand what knapsack is? What is the difference of the problems? One, I've got these values and weights, right? Any questions? So which is Bandersnatch and which is mobility? Which is Bandersnatch in this case? I want everybody to think for a moment. Which is Bandersnatch, knapsack or integer partition? We count to 3. 1, 2, 3. Who here says that Bandersnatch is subset sum? Who here says that Bandersnatch is knapsack? Well, which is the known hard problem? Is it knapsack or is it subset sum? Subset sum is the hard problem. That's what I did yesterday with the graphs, right? So is that one Bandersnatch or is that one? Bandersnatch is the hard problem, right? So I've got to prove, how do I solve subset sum which is where I am given, actually, or integer partition is subset sum, excuse me. Now this is subset sum, excuse me. Subset sum. I'm given S and I am given T. And in order to solve that, I've got to now show how I can use that. Use knapsack to solve it. Where I'm given a collection of integers, of items which paired basically, cost and size. And I have a bound on the total knapsack size and a bound on the total cost I want to get. Okay? Do you see what I'm now trying to do? I want to show that my known hard problem, which I proved last class, subset sum, I can that I could solve subset sum by using the right knapsack solver. Okay? Any questions about the general strategy? Okay? I want the general strategy clear here. And the only reason why people, I think, are getting nervous is these problems smell so close already. Okay? Or maybe not. Okay? Any questions about the general strategy here? Subset sum, remember, was a collection of integers and a target. Can I make them add up to exactly the target? Okay? Knapsack, can I find the subset of items where each item has a cost and a size? Okay? Such that I can fit within this cost bound and I get a value of at least that. Okay? Any questions? So how do I do it? Does anybody want to propose a transformation? You need to be able to come up with, I want to convert these numbers into pairs, okay, where every item has a value and a size, yeah?
The weight of each object in subset sum, make that also the value of that object.
Okay, so you want me to say is to take, for S prime, you want me to take every element from this and say that I'm going to create pairs where the weight is going to be SI and the value is going to be SI. Right? Did everybody see what he's done? He is saying basically that this stuff is like gold. You pay, say, a price per pound, right? And that the cost in his instance, every object is going to cost the same as its weight, basically. It's going to cost $1 a pound. Okay? Any questions? What is K going to be, which is the knapsack size bound? T. And this is going to be the basically capacity of the knapsack. I don't know, I get confused what K and B are. Capacity of the knapsack. Right? B is going to be the value, the minimum acceptable value. You get punished if you don't come home with that many dollars worth of stuff. Okay? Any questions? What is this going to be? This is also the target. Let's think if this does the problem. Suppose we get a knapsack thing, meaning, suppose we find a collection of something that weighs at most T that gives us a value of at least T. Right? Isn't that what this is really saying? If we found a collection of items whose weight is at least T, at most T, and whose cost is at least T, whose value is at least T, that is possible only if the sum of the weights and the sum of the costs are exactly T. Does everybody see that? So in fact, if we find something of at least a value of T, I mean, it's easy to get something of at least a value, steal everything. But it's got to weigh at most T. And the only way we can get at least T dollars worth of stuff that weighs at most T pounds is if we get exactly T dollars worth of stuff which weighs exactly 3 pounds. And that's exactly what is being asked for here. Okay? Does everybody see that we are solving the problem we had yesterday? Okay? Using knapsack. Okay? How many people see this? Okay? Any questions about this? The only concern here is this doesn't look that big an accomplishment because knapsack seems like a more harder problem than this. Okay? But does everybody see what the reduction is? This would have been a perfectly fine homework problem. Too bad we picked it in here. I could have given it on the final. Okay? Any questions about this reduction, how it worked? Okay? Again, the design of this thing flows logically from what we are doing. Okay? Any questions? Okay? Do we want to, I'm going to give you now 2 choices here. Okay? We went through this quicker than I thought because this was an easy one. Okay? Do you want me to do another one, or do you want me to spend more time telling you what P and NP are and things like that? How many people here want to see another one? A bunch. How many people want to see more about NP, P? Not so much. Okay? Okay. You. Pick somebody else. Somebody stand up. Okay? Somebody stand up. You stand up. Pick somebody else. Pick somebody else. Anyone? Okay, you. Okay? Whoever was pointed to, make sure they stand up. Okay? Someone who he was picked. Somebody else. That's going to sound like I got stooges here, it looks like. Yes. Okay, you're standing up. Okay. Now, which do we want in this class? Do we want a graph theory problem? How many people want a graph theory problem this time? Not too many. Okay. How many people want a network design problem? We got that. How many people want a storage problem? How many people want another set? Wait, what's the other ones? Set and partitions. Okay. And how many people want another mathematical programming? Nobody. Okay, which one got the biggest crowd? Graph theory. Okay, how many graph theory problems are there? 11. Uh-oh. Pick one of the ones from number from 1 to 11. 5. What's the 5th one on the list? GT23. What is GT23? 196. What does this say? Uh-oh, this one sounds bad. What does this one say? Induced path. What does this thing say? It says that we are given a graph, and we are given a, this one actually does sound bad, okay? Given a graph and a positive integer. Does there exist a subset of vertices such that that subgraph is a simple path, okay, on those vertices? Okay, so let's look at what they are asking here. Okay? The problem is the following. I am giving you a graph. Here is a graph. Let's say the following. Here is a graph. Does everybody see this graph? Okay? The question here is does there exist, I give you a graph and I give you a K. And the question here is, let me first give you a simpler version of the problem that you understand because we just talked about it. Is there a path of visiting exactly K vertices without repetition in that graph? Okay? Yes. So there's 2 problems here, right? I'm going to talk about. There is what we call this thing path of length K and induced path of length K. The simpler one, which is not what was being asked for, but let's just talk about it, is there a path of length K? Is there a path in the graph that visits, let's say, 3 vertices, okay, without repetition? Is that true in this graph? The answer is yes. Ka-chunk, ka-chunk, ka-chunk. Does everybody see that? Okay? Is there a path that visits 7 vertices? Probably 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We could even visit all 10 vertices on a path, right? If I ask, this is a problem I was just talking about in a minute ago. If I ask, does there exist a simple, meaning without repeating vertices, path of length k? Okay? Suppose that was the problem that was being asked. Is that problem NP complete? Is that problem hard? Okay. Where we're not allowed to repeat vertices? Yeah?
I think we can solve this one just by finding a minimum spanning tree, can't we?
No, you're saying a minimum spanning tree. A spanning tree might look like this. Doesn't have a long path to it. Right? Does everybody see that? Finding a spanning tree is not hard. Finding the shortest path between 2 vertices is not hard. Right? Finding the longest path where you're not allowed to repeat vertices is what's hard. Okay? Yeah? Couldn't you do 2 depth-first searches? You're saying, wait, he asked me to do that on the homework, and it wasn't hard on the homework, right? Why wasn't it hard on the homework? I asked you to find the longest path in a graph, right? But what kind of graph was it? A tree. So finding the longest path on a tree is not hard. That can be done by a depth-first search on the graph, right? You're going back and forth, right? In a tree, there's only one unique path between any pair of vertices. So trees are very simple. And so it is quite possible that there is an algorithm to find something on a tree that might be hard to find in a general graph. Does everybody see that? That's an important point to see, right? Now, can you argue with me that this problem is hard? Find a simple path of length k, yeah? Isn't this just like Hamiltonian path? Right? What would we be saying? This would have been simple path of length of a graph G of length k, right? The claim would be that what's our Bandersnatch going to be? I almost got confused there. My Bandersnatch is going to be Hamiltonian path of a graph, right? I want to now use, is there a way to use simple path in some other graph G prime of length k? And you're going to tell me, yes, use the same graph, G prime equals G, and set k meaning visit all the vertices, right? Does everybody see that? So, if our question is, if we have a subroutine that given a k and given a graph G prime, we'll find, is there a path visiting k vertices, different vertices in there without repetition? If we can call it for any graph G and any size n, say, yeah, take this graph you want to find the Hamiltonian path for. Ask, does this graph have a path of length n, where it visits n vertices without repetition? The only way it can find that is if you have a path that visits n vertices without repetition. You have a path that visits all the vertices without repetition. And that is exactly what Hamiltonian path is asking for. Does everybody see? This is another very simple reduction. Okay? Isn't quite the problem we wanted to solve, however. But I want everybody to see where we are now. How many people are with me at this point? Okay? It should be clear how we did this one. Does everybody see now? Hamiltonian path. That sounds like a hard problem. Skinner says it's hard. He didn't prove it for me, right? There's another one of these horrible constructions where you can take it and show that, that's a fairly tricky thing to prove that Hamiltonian path is hard. But I know it's hard. You can look it up in Gary and Johnson here. You want to see it? Look in here. Okay? Does everybody see how now the problem of does there exist a simple path of length k we showed hard using this construction? How many people understand that? Any questions here before I go a little further? Yes?
No,
Any questions here? At the risk of going a little further, though, the disappointing thing is that isn't the problem that was in the book. The good thing is I've just proven something hard. I've proven two things hard from scratch while you were here, right? The disappointing thing is it wasn't quite the problem in the book. What did the problem in the book say? The problem in the book said induced path. What does an induced path mean? It means does there exist a set of vertices, okay, such that there is no, that if we take these vertices, there are edges forming a path, but no edge otherwise shortening the path. Okay? So what does this mean? In this vert graph, does everybody see that there exists a set of 4 vertices such that there is no shortcut between them? Right? There is a path here of length 5 such that there is no shortcut. Right? Does everybody see this? There is a path of length 6. Okay? Can I pick this extra vertex, or will that cause a shortcut? Does everybody see that would cause a shortcut? Right? I could, I guess, also pick this vertex. Can I pick this vertex? Yes. Okay? So an induced path is a path with the property that the vertices in it form a path, but there's no other edges in that. Okay? Any questions? How many people see what the problem is? So in this case, there is a problem where the longest path is in fact longer than the longest induced path. Okay? Any questions about that one? Now this sounds like a much harder, this one problem sounds a lot weirder now, right? So let's think about it. Any questions about what the problem is? Okay, let me think for a minute now. Can we come up with a reduction for this? Okay? Any questions quickly? Just think for a minute. How might one do this kind of thing? So what am I thinking? I first have to think, what is my Bandersnatch and what is my mobility, right? Let's go to the blackboard here, maybe to start doing this thing a little bit. What is my Bandersnatch go? My mobility is going to be induced path, right? So what do I want to do? Okay, I guess I may want to get rid of that, clear it anyway. I guess, okay, that doesn't work. Okay, let me do it this. Okay, sorry, it's going to go here. Okay, what is it that we can do? Okay, we want to now prove for some problem that is there an induced path, okay, in a graph G of length k, that this is the same as some hard problem. Which hard problem sounds most familiar to people like this? Which hard problem that we have? Okay, let's take a vote. Does this smell like satisfiability? Does this smell like vertex cover? A couple people. Does this smell like, see, it says vertex cover. Why does it say vertex cover? It's a graph, and it has to do with a subset of things, maybe you're thinking. Okay, that may be an analogy. Who do they think it smells like a Hamiltonian path? Well, now you sense the path, you sense the ordering. Okay? This is a hard one. Let me think for a minute. I encourage everyone to think for a minute. I haven't quite decided where I want to start yet on this one. So let me think for a minute. Well, let's think what I want to do. This is a tricky one. This, frankly, is a very tricky one. Okay? And I've only got about 15 minutes, so we're in a little bit of trouble here. Okay? Let's think about this if I want to do this. See, it's hard here because I'm not coming up with what I think is the really right way to start from it. Okay? Because there are a couple of different candidates, all seem to have merit. That's why I'm a little bit distracted. Let's start thinking about Hamiltonian path. Okay, or longest path of length k. Okay? I can ask, is there a path of length k? Okay? I'd like to find some way to take a graph where you're looking for, is there any path of length k? Okay? And do a reduction where there is going to be an isolated path, if there is one. Okay? An empty induced path here. Can I think of a way to do this thing? I'd like to sort of get rid of, say that if there is a long path here, I'd like to get rid of those edges. But I have to somehow translate the graph so it doesn't have those edges. Okay? And that seems like a hard thing to do. Okay? I'm not sure I'm seeing anything yet. Do you see what I'd kind of like to do? I'd like to take my graph G, translate it into a way where there's going to be long induced empty paths. One way I could do this is to take every edge that I translate and add a lot of vertices in between it. Does everybody see that? If I took my graph like this and I translated it into something like this, where for every edge I replaced its edge by a chain of 10 vertices. Okay? Now, if you had now there's going to be long induced paths, but the trouble that still remains is, if there is something that is going to bypass it, okay, one of these bypasses is enough to break that thing, and I need to assemble a lot of edges together. Okay? So this isn't doing it for me. Okay? Any questions now? What about vertex cover? Let's think about vertex cover for a second. Vertex cover is saying I am given a graph and I am picking, okay, a collection of, I'm asked for a subset of vertices such that all the vertices that I pick, okay, are going to, that all the vertices I pick are going to cover all the edges. Now the trouble with vertex cover is a min problem. Whereas what makes it hard here is that this induced path thing is a max problem. You see, it's easy to find a short induced path, just one edge. It's hard to find a long thing. Okay? And so I want to try to think, are there anything like vertex cover that's a max problem? Well, clique is a max problem, right? Kabunk, kabunk, kabunk. How would I like it to be the case that if there was a clique, okay, that I would have a long path here, okay, that was induced? And I'll admit that I'm not really doing it. But what about independent set? Independent set is a similar kind of an idea, right? Where there are a bunch of vertices that don't have anything in it, right? What if I did the following, however? Maybe this is going to do what I want. What if I had a big independent set and I had another vertex out here where for every edge that could have been in my graph, kabunk, kabunk, I go out to another place. Okay? Now maybe this I'm starting to think about. Hold on a second. Suppose I build a graph where here is my graph G, okay? And here happens to be an independent set, and here happens to be some other things in it, right? What if I create another set of m vertices, one for every edge of my graph, okay? Such that, okay, for every edge, this is the edge 1, 2, I have a vertex here 1, 2 that goes like this. Here's another edge in, okay, I guess there's, for every non-edge of my graph, let me put it, for every non-edge in my graph, okay, these are going to be the n choose 2 minus m non-edges. What am I doing now? Let's do, I don't know how many people, okay, I'm rambling, but now I think I have an idea. So let me explain my idea. It might not work, but let me explain my idea. I am going to take a graph where you're trying to find an independent set, right? And for every non-edge of the graph, okay, I am going to create a vertex for every non-edge of that graph. Here is a non-edge of that graph, right? I am going to have as the endpoints of that, this is a non-edge ij. Okay? What is interesting about this? Okay? Suppose you have a big, okay, empty, Suppose you have a, an independent set here. Does everybody see that a walk through the edges of that independent set is going to yield a large number of vertices? Let's say that we take a path. Let's say we have an independent set of the graph. That means that there's no real edges between them, right? We're going to look for, is there a path that is going to take me for a set of vertices through k of these non-edges, okay? That path is going to be, I claim, an induced path, okay? How many people are seeing anything of what I'm seeing? A couple people. Let me try to see it again and see if we're nailing this down a little bit. What are we looking for? We are looking for a chain of vertices with the property that there are no shortcuts, right? I'd like to now show, let's see what I'm trying to do now. I am trying to show you a way to solve an independent set problem in a graph G. Okay? Is there an independent set of size k? And I'm going to try to do it by solving independent path on a graph H, where what H is going to be is equal to G plus, n choose 2 minus m vertices for non-edges. Does everybody see my construction? For every non-edge, I'm going to create a new vertex. That vertex is going to be created, be adjacent to the two vertices that were that non-edge in the original graph, right? So my graph is going to be my old graph G plus a lot of these isolated vertices, right? Does everybody see that? If I'm doing this, what's good about it? Anytime I go on a path that goes ka-chunk, 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 there can't be any shortcuts, right? Because these vertices are alone. There are not going to be any shortcuts whenever I take a trip up to one of these guys, right? But in order to take a trip to one of these guys, I'm going to have to move from this to somebody else, right? From this shortcut to another shortcut that takes me to a different vertex, right? if I have an independent set for real of size k, then I can take a walk through k of the non-edges. And this is going to have to be an induced path. Why is that? Certainly there's no shortcuts between any of the two vertices I'd added. By definition, there are no shortcuts. And if this is an independent set, what does independent set mean? It means that there is no edge that goes between two of those vertices. Isn't that what an independent set is? Yeah?
Are you getting rid of the original, in H, are you getting rid of the original edges from G?
No, I'm keeping those edges.
Then what if you found an induced path through a G?
Okay, so there may be, first understand my logic. There may be a couple of exceptions I'm going to have to deal with, but there is a big picture of logic here that is right. Okay? What am I trying to say here? If you do this graph, does everybody see that if there is an independent set that is large, there is going to be a large induced path? Okay? Because the path that I'm taking you to is going up to here, down to here. Up to here, down to here. Does everybody see that? So the path that I'm talking about, if you have an independent set of size k, these are the k vertices on that path, right? Because an independent set is made up of non-edges, okay? Then for every non-edge, I had a separate vertex adjacent to the two edges of that non-edge. If this was an independent set, then there had to be a path that visited those k vertices, each by taking one intermediate non-edge hop. Okay? And what's more, this path has the property that it is going to be an induced path. There can't be any shortcuts between any two vertices that I added here. There can't be any shortcuts between these two because this is an independent set. Okay? So what I think I have just demonstrated is that in this graph, if there is a large independent set, there will be, in the original graph, there will be a large induced path in this graph. That, I think, is now clear. Any questions about that? Okay? How many people see what I'm saying here? Okay? The other part that still, I think, details we have to work out and will not work out in the next couple of, 2 minutes before we leave, is we have to then show that there's no other long induced path in this thing. Okay? And I argue I may have to add a little bit of something to make sure there's no other long induced path. Okay? Actually, the way that I can probably do that, by the way, is with my subdividing trick. Suppose I don't make this just one thing. I make it a zillion independent vertices here. Now, if you want a long induced path, you had better use as many of these other guys as you can. Okay? And now I think I have done it. Do you sort of agree with that? Okay. Neat, sweet, NP complete. Okay? Any questions about it? People see what the logic is before we go anywhere. I'm not asking you to do this one on the final. But you see how there was it ultimately isn't that complicated. If you see the problem the right way with the right analogy there. Okay, any questions about this or anything else? That said, final exam, Monday the 20th, 5:30, Benedict. Okay, roughly 9 problems, like the homeworks, do the best you can, good luck, see you guys then.